Why do some vices cost more than others? I've received a lot of comments over the years asking, why would anyone spend money on a hardtail vise when there are just so many used vise options out there that seem to work just fine? And that's exactly what we're going to answer. So I want to justify and help you guys understand why the price is where it is, with two vices that look similar at a glance, but perform dramatically different. All this actually started a long time ago. For a very long time, vices were categorized by their jaw size and how far they opened. For example, a 2-inch vise was smaller than a 4-inch vise, which was smaller than a 6-inch vise, and so on. If you bought a larger jaw size vise, you'd expect a bigger, stronger tool. But after World War II, a lot of manufacturers started taking advantage of that. In many cases, they kept the jaw size people recognized. They would use less material, shrink parts of the vise body, simplify the castings, and make manufacturing easier and cheaper, while still marketing the vise by the same jaw size. So now you could have two vices that were both called 6-inch vices, even though one of them was built much lighter than the other. And that's where the confusion really starts. Because on paper, they sound comparable, but in the real world, they aren't. These vices would work fine for light-duty jobs, but when people started pushing them harder with more clamping force, more hammering, more bending, and more abuse, the weak points started showing up fast. And for people using vices in high-pressure situations, this became a real problem. Because when a vise breaks, the work stops. So a high-pressure vise is not for everyone. But for people who really do need it, it really matters. For the people who rely on that clamping force, that durability, and that reliability, it becomes a completely different class of tool. So is it worth it? How much better is a high-pressure vise than a general-purpose vise? So does performance actually justify the cost? Well, to find out, I'm going to run a series of tests to see how these vices handle hammering, bending, torque, and the kind of work that exposes weaknesses fast. But to do that, I need a vise to represent the general purpose category. And if I'm going to make that comparison, it needs to be a vise that people actually respect. Something with a real reputation. Something used by people all over the world. For that, I'm using the record number 6 vise. This design started being produced in England in the early 1900s. And built a reputation that's lasted generations. Collectors love them, fabricators still seek them out, and even though the last English-made record vise were produced over 20 years ago, vintage records are still popular for this reason. And for the high-pressure vise, I'm going to be using the Fireball 510 Hardtail. This vise was designed for serious work. Whether it's in the shop or in the back of a service truck, it was built around the idea that when you need real force and real durability, your vise should be able to deliver it. But like everything else we do here in the shop, that needs to be proven. So let's compare a general purpose vise to a high pressure vise. I'm comparing an apple to a blueberry. These two are not the same, and I want to show you why. First, let's unbox a brand new Fireball 510 and weigh it. And the 510 weighs in at a hefty 144 pounds, or 63.5 kilograms. Now for the record number 6, which weighs in at 85 pounds, or 38.5 kilograms. So next, let's open these vices up to their max. Opening size is this distance right here to here. And all we have to do with this vise is just measure the distance hanging off the back here. All right, so this vise has an opening size of 8 inches. Remember, that means that this vise cannot open up any further because we lose the purchase area on the back of the vise. All right, let's measure the Fireball Hardtail 510. All you have to do is measure from flange here to flange, and you can see we're at over 12 inches of opening. Even though we call this the 510, I cheat and I added 2 inches of opening size to this. There's 12 inches of opening. And that's what you want in a vise. You want versatility. Okay, there's the two, side by side. Just remember, when you're doing real work, you want as much capacity as possible. Why would you want that? You could put more stuff in between the jaws. This is like truck world. A long bed versus a short bed. You can put more stuff in a long bed. The truck is more usable. And now, let's take both vices apart. There's something keeping the dynamic jaw inside the static jaw. So let's just pull the pin and we'll pop it loose. Okay, careful not to lose the pin. There we go. And now this whole thing should come out. See, look at the inside of this vise. See how yucky it is? Look at the screw. Because it's open to the elements, really makes the vise not fun to operate. Where the hardtail is covered. It's completely sealed. This and the opening right here are the only two entrances for stuff to get into. Completely two different designs. One is a C shape. This one is four-sided. So which is better at resisting forces, a box tube or a C shape? Whenever you clamp something really hard in a vise, the jaws want to go down. So the tube design is important for resisting these forces. In a C-shaped design, when you press down, the top of the C is in tension, but there is no bottom to compress. So naturally, the C shape is easier to bend. This is why you see so many C-shaped vise design break under high loads. If you need to clamp off-center in a vise jaw, you've now introduced a completely different load from another direction. The vise has to resist those down forces as well as side forces. In the Fireball box design, the top is trying to stretch, but the bottom is there trying to compress. And the sidewalls are there to hold it all together. 4 sides of the box tube also helps resist side forces. Let's measure wall thickness. That's exactly 1/2 inch. Or 12.73 millimeters. Wall thickness on the Fireball, also 13 millimeters on the sides, 23 millimeters on the top. So let's look at overall height of the slide. We're approximately just under 4 inches tall. On the record, we are just a little bit over 3. We're looking at 3.5 inches for throat. And the Fireball vise is also exactly 3.5 inches. Next, we are gonna be looking at screws. So first thing you're gonna notice is, wow, that number 6 has a very fine thread. All right, let's look at the Fireball. This is called an Acme thread. The main difference between these two screws is how many starts they have. The Fireball has 1 start to the screw with big chunky teeth. The Record has what we call a double start, where another row of teeth is woven between the first set. This is still a coarse thread design, but allowing a smaller tooth. So what we're gonna do, let's just check thread pitch. What that means is how far does the jaw advance for every twist of the screw? Obviously, if a screw has more threads per inch, it generally is easier to turn, but at the disadvantage that it takes more turns to move the jaw. So we have a dial indicator inside the jaws, so we can measure how far the jaw advances for every rotation that the handle moves. Okay, we're at 0 right there. Let's make a mark. So when these come back again, we're gonna measure how far the jaw has moved. Here we go. 1, 2, 3, 4, coming up on 5. That's 5 turns. For every turn of the screw, it moves 1/4 of an inch. So that means we've advanced 250 thousandths of an inch. Let's check the 5/10. Okay, there's 0. Let's make a mark. Okay, we got 1, 2, 3, 4. Would you look at that? 5 turns. Exactly 1/4 of an inch. So this is a pretty fast acting vise. Exactly the same as this one. The next thing we're gonna look at, how the screw interfaces with the jaw. This part of the steel pushes on this part of the casting. Metal to metal contact. So remember, as this is getting squeezed together, you have a lot of friction right here. And you can see that somebody really had a hard time turning this. Look at the shape of the handle. They were struggling to get the clamping force that they needed. This spring right here goes on the inside. So as you back the screw off, it's pulling on that pin. That may not look like a weak point to you, but I have done lots of testing and this might shear right there when we put a lot of load on it. Let's look at the way the Hardtail does it. We have 3/4 of an inch thick casting right here and a provision for a thrust bearing. This is a ball bearing thrust bearing. These can take upwards of 45 to 50,000 pounds of force. This casting right here is sandwiched in between this thrust bearing and this thrust bearing, and then it's held in by this macho collar. This pin and this collar are doing the same thing. The beauty of this is that it does not drill a hole through the spindle. This captures on the outside. There is no hole. There is nothing to cause a stress fracture of any kind. Literally pinches on the screw. Now let's look at the engineering between the static jaw of both of these vices. We got nice big front cheeks up here. Okay, we have a nice chin that sticks out the front. As soon as you start clamping, the vice jaw wants to go down, and this is a good support for that. The other purpose of this part is to hold the nut, and this is what keeps this part from tipping out. This part engages up here in front, and they do all of this being as cast. It keeps more money in the company's pocket if they don't have to machine anything, but the trade-off is you get a little bit of slop. This dovetail breaks out, which means this casting snaps. You're pulling, you're pulling, you're pulling, pump, and it pops. What I don't like about this style is we get something called screw bind. So I've modified this vise for this demonstration. I've replaced the regular screw with this little 1/4-inch rod because it's easier to demonstrate what happens. So watch what happens when we start to clamp something. The screw is nice and straight, right? Straight through here. I'm going to start clamping this part. Now watch the screw in the back. See it starting to lift? Look at what's happening. As I start cranking harder and harder and harder, this nut is tilting forward, causing the screw to get misaligned. So this screw is doing this. It has a nice big bow in it. The tighter I squeeze, this screw is now becoming a U shape, and that puts the screw into a bind. And you've seen this in a previous video with the Morgan vise, is that the screw will snap off because it binds up. Does it work? Yep. The manufacturer does this because it's cheap and it's easy and they want to put profits in their back pocket. The Record has no anvil in the back, so they're able to keep the body a little bit shorter. But that didn't stop whoever owned this before from doing some blacksmithing. What they've chosen to do is use the back of the slide as an anvil. Bang, 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 bang with the ball peen hammer. Look at all that stuff. Obviously they wanted an anvil. They're just using the back of the slide. This is bad practice. Do not hit this with a hammer. So it's unfortunate that the Record vise doesn't have a place for somebody to tap on. So let's look how the static jaw holds on to the dynamic jaw. Obviously we have the floor, one here on the chin, and 2 little pads here on the back. That keeps it flat. They have just chosen to have a machine surface on the top, a machine surface on the sides. There's no pad or machine surface down here at the bottom preventing the rolling. So let's look at the Fireball vise. Once again, we're very similar in size. We have the same height and the same throat depth. The shelf is longer. The Fireball has a longer chin than the Record. It has pads on the bottom, machine pads on the top and on the sides and on the back. The other thing you're going to notice about the static jaw is the Hardtail has an anvil on the back. That way you can do some blacksmithing. So the threads are at the very end of this long tube on the Hardtail vise. This is what allows us to have a rectangular slide. We're able to hold the nut from the end, and this is what gives us this fully boxed dynamic jaw. What holds this tube nut in is the Hardtail. This protects the slide from getting yuckum in it, and it allows for perfect alignment with the screw. Pulling from the back of the vise, the center line of this screw will always remain straight. There's a groove in here. It matches this groove right here in the bottom. It's just one extra layer of machining that we put into this vise to help counteract the roll. See how tight it is? There's 0 roll in this. The next thing we're going to look at is the swivel base. You loosen these knobs and then you can pivot this vise around this piece of casting. And then this piece of casting is bolted to the table. So let's pull this off. You can see some nice machining inside of here. We have pretty thin castings. I've seen ears break off right here. 5/8 of an inch ears. The diameter of the ring is very important for work holding. The larger the ring, the more force it takes to twist it. So let's compare it to the Hardtail. It outweighs this one 3 to 1. The overall footprint is huge, 10 inches by 6. We can bolt this down to a fixture table. What holds the vise down to the swivel base are these tapered nuts. And as you can see, as they roll around, they grip the inside of this solid with the outside. And these tapered nuts wedge up there. Now picture this. We're trying to design this vise to be on the back of a service truck. The possibility of getting stolen is high. Watch how easy it would be just to steal a body. Turn these knobs. There you go, he's out. I just showed you guys how to steal vices off service trucks in 20 seconds. This is the pivot pin. So as you can see, both the handles are out. It can swivel freely, but we cannot remove it off the bench if these were welded down to the table, the bolts, like they would be on a service truck. Even if they take the hardware off, they cannot get to this nut, which means they cannot lift the vise off. They're gonna get away with some handles, but they can't steal the vise off the back of the truck. But these are easily replaceable. Let's look at the hardware. This is a little mini meatball. This comes loose if you want to replace it. Let's compare them side by side. This is made out of all one piece. This has a little tiny pin in here. I guarantee if you push this hard enough, we could probably spread it and get that pin to break off. Let's take a look at the jaws. That's just a piece of 1 by 1/2 inch flat bar. We've seen this a lot where these snap. Everybody's done it. These are in here and you're gonna hammer down. It puts a lot of stress right there on the inside corner. Inside corners are bad for stress risers. So we have small screws, small little shelf. There is quite a bit of meat underneath here, but in my testing, these will split right here if you do a lot of hammering. Okay, let's take the jaws off of the Fireball vise here. Here is the Record, here's the Hardtail. You got a 1/2 inch bolt and a little tiny 5/16. Now this is a jaw. This is over 1 inch thick. 1, it's not gonna bend. 2, if you wanted to resurface it and re-knurl it on the milling machine, you can do that. But the next cool thing you're gonna notice is this hook on the back. The hook's on the back of the casting, and now, as you put something in the vise and tap, 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 it's transferring the load all the way down this entire casting. If you want to build your own custom set of jaws out of a piece of 1/2 inch bar or 3/4 bar, you have a shelf also. So the beauty about having a brand new vise like the Hardtail is you get support from Fireball. We have options like this, a set of soft jaws. These are my favorite, because if you're clamping onto small screws, nuts or bolts, you can literally pinch onto the threads and not damage anything. Did we put a little nick in the jaws? Absolutely. We can resurface these, we can file things flat. That's the purpose of a soft jaw. We have V-jaws. If you do a lot of round holding, tubing parts, that's another benefit of having a nice, fat, wide jaw. We can put features like this into the face of the jaw. Or something like this. This is a smooth, hardened jaw. Something like you'd see in a Kurt milling vise, where you really want a hard, smooth surface. And we've machined this little tiny step in the top. Maybe you need to do some work on a piece of sheet metal. They sit here on the shelf, you can clamp it, and now you can drill, tap, and go down without it flipping in the jaws. And then of course, an offset jaw, because a lot of times you might want to be working off the side of the vise. So what this allows you to do is shift all the offset of this longer jaw to one side. We get a lot of overhang off the side of the vise, and depending on what side of the vise we want to work on, we can shift the offset over. A lot of you say the Hardtail vise is too big, it won't fit on the standard workbench. Standard workbench is 2 feet and the Fireball is only 19 inches long. That's where the back of the vise is. This vise opens up to 12 inches, but at the trade-off, the back needs to get a little bit longer. So engineers are always faced with trade-offs. We could shorten this jaw up to reduce the amount that sticks out the back by 2 inches, but I would rather have more room up here. The relief underneath here from the tip of this jaw back gives us more relief for bending. Or piece of channel iron, okay, with no extra tools. If I want to hang on to this piece of angle iron, it goes under the jaw, and we can work on this surface right here. The number 6 just doesn't quite have that room in there. I am forced to hang on to it like this, or up high on the piece of angle iron. So your work holding is above the jaws. But what happens if whatever the feature is requires you to be down here? It wants to roll it. I want to be able to hold as much stuff as I possibly can. I don't want to be limited by this tool. So now let's look at handles. The handle on the vise is one of the most important features. It protects the vise from getting damaged. This is the tool that we use to interact with the screw. Now, if we want more force or more pressure, obviously the longer lever we have, the more force we can apply. But naturally, the vise can only take so much input. So as a designer, we design the vise handle length to accommodate that. And in this case, this number 6 has seen some better days. Look at all the hammer marks on it. All these hammer marks are from doing this. And it's because that this vise is not producing enough clamping force. That's the other thing too, is once you hammer it tight, can't get it loose. Which inevitably put the cheater bar on it and we get bends like this. It's not replaceable, they've swedged it on. They've mushroomed the ends. We have to literally cut this handle off to replace it. So then the next thing you guys say, let's just put a longer handle on it. Sometimes this distance is really short. You have to start choking up on the handle. Well, the longer handle just gets in your way. So getting some space between the handle and the back of the jaw, it just increases your capabilities. So now let's look at the Hardtail vise. Completely different looking for one. So we've had to reduce the diameter here so that the handle bends before we do internal damage to the vise. But we need to keep that diameter large because it fits in our hand better. But the other thing that this vise has got going for it is that we can remove the handle and replace it if it gets damaged. You got the ends, you got the little knobs, you got the rubber bushings that over time you can replace them so they don't smash your fingers. Nice meatball here that's been hardened. The distance between the handle and the back jaw is much greater. This allows us to actually spin the handle without interfering with anything. And having the center line of the vise handle low to the jaw, that's also a good feature. We want to be able to hang stuff over and around. Next, we're looking at what does it take to bend this handle. Okay, so let's put the load cell in between the jaws here, and we're going to crank it up by hand, and then I'm going to hit it with a hammer. Okay, that's as far as I can go with my hand. That's 5,000 pounds. All right, let's start whacking it with a hammer, see what we get. 7,000, 8,000. I'm gonna hurt myself. 11,800. Smashing it with the hammer. Let's bend the handle with this. Ready, set, go. Oh, 13,000, 13,000, 14,000. Bending the handle, 14,000. Bent the handle. Let's just keep going a little more. There we go. That's a pretty good bend. Peak value, 14,464 pounds. That's what somebody needed in between these jaws to do something. They were trying to squeeze something this hard, like pressing a bearing, but they needed that much force. Let's release the pressure because this is a ticking time bomb right now. It could explode at any moment. Still works. That's a serious bend. So here's the deal. When I designed the Fireball 510, I designed it to hit those pressures without any cheater bar or hammering. Okay, we got it loaded up. No cuts this time, editor. Here we go. There's 14.8 and another good jerk. 15, 16, 17, 18, 19, 20. That's 20,000 pounds without a cheater bar. This is pretty standard stuff. I see this every day. Let's release the handle a little bit and show you how easy it is. This handle isn't going anywhere, it's tight. But with a good stiff pull, it comes loose pretty easily. Okay, and there we go. Now that we understand the design differences between these two vices, let's put them to the test. Let's see how they perform under real-life situations that would require high amounts of pressure. The first real-world application test that I want to try is to simulate twisting off a cap off of a pipe. This will require lots of clamping force to hold the cylinder in place, and we can simulate this with a hardened steel cylinder and a torque wrench. Record gave us 6-inch jaws. I want to hold it right here on the very edge as far out as I possibly can. Maybe we need to fly past the jaw for some reason and hold a long cylindrical object. But we're going to use a much shorter piece just for fun. And then we're going to apply this torque and we're going to see how high this load cell goes off before this starts to slip. We're going to clamp it right in here. I'm going to crank the handle as hard as I can. I might even hit it with a hammer. Okay, I'm going to push till it falls out. All right, so let's rewind the footage, and as we can see, as the socket gets ejected out of the jaws, we could see 113 foot-pounds of force to twist that right out of the jaws. All right, let's do the same thing on the 510, but guess what I'm gonna do? I'm gonna grease the socket. Every mechanic knows their sockets look like this when they're using it in the vise. I'm gonna completely handicap the Fireball 510. Now let's hang on to it. Another thing I'm gonna do, I am actually gonna hold this socket just slightly off of center, the wrong direction. And as you can see, we are barely hanging on to that sucker. So I'm gonna pull on the handle as hard as I can. Just get it nice and tight, just like I normally would. Tight, no hammer, no nothing. Let's pull, twisting hard. Okay, we're overloaded. Come on! Way overloaded. Well, that last test really didn't go to plan, so I want to do it again. The previous load cell, that didn't go high enough. I want to see an actual number. And we should be comparing new jaws to new jaws, right? That should be only fair. So what we've brought in is a brand new record vise. Unfortunately, they don't make one in England anymore. You got to go somewhere else, but what it does have is brand new jaws, and this design is exactly the same as before. Because we got our good load cell here and a brand new torque probe. This is good for 1,000 foot-pounds. Look at this freaking load cells, 1,000 foot-pounds. The other thing we're gonna change is socket. This is a chrome socket, harder to grip onto. And we got the high-speed camera here, so we'll be able to see if anything blows up. So we're gonna do the same thing as we did last time. We're gonna pinch it right on the edge. I'm gonna come right up to the top. I like that. The socket's just inboard of center line, just by a little bit. All right, I'm gonna pull as hard as I can. And then for safety's sake, a bigger hammer to the handle. I think that's pretty tight. So what I'm noticing is the jaws are going like this. So this distance on this side of jaw is smaller than over here. So the jaws are not parallel when you clamp on the end. Okay, here we go. Oh, it's twisting. It's rolling backwards. Come on, baby, stay in the thing. I think we've all experienced this before. No, it just wants to rotate out. Man, she was wiggling a lot. Wow. Okay, I got the chute out of there at 236, and I completely flattened out the jaws. There's the socket. Put some knurling in there, so we were gripping pretty hard, but it still wanted to wiggle around in there. You saw that first initial hit, how it was just sliding. That's not convenient when you're trying to loosen or tighten something spherical. So here's what I want to do. I want to run the test one more time now that we have flattened jaws. I mean, realistically, you're not going to switch out to a new set of jaws every single time you do this. So let's do it one more time on a new part of the socket. Do the same thing again, as tight as we can get it. I've seen you do it before. Don't lie to me. Okay, I'm going to wrap some tape around this so that it doesn't come off this time. All right, pulling. Oh, it just wants to roll out again. Come on, baby. I'll go this way, I guess. Woo! Oh, that almost hit the car. Jeez. Boom. I mean, that just shows explosive force, right? That it's like, hey, Jason's not cheating here. Once again, the jaws are rolled. Boy, that's sharp right there. Whoosh. You probably can't see it on camera, but the handle is definitely bent. So we were at maximum clamping force and then some, well beyond its rated capacity. Same socket right there that doesn't have any knurling on it, and I'm gonna grip onto that part right there. We're gonna select a clean, non-knurled section of the socket. Okay, there we go. So I'm just gonna push this down by hand. Just gonna give it a good little tug right here. Just like that. Oh, jeez. Whoa. Oh. Jeez. Okay, that's a good number. 282. So here's the socket. Let's wipe this off. The knurling isn't nearly as destructive. 1, 2, 3, 4, 5, 6 places versus chowder. So did you notice as I was pulling on that, how stable that was? It wasn't walking all over the place. It wasn't wiggling like it was in the record vise. This was just stout. It did not move. It did not wiggle. Hard yank just to get it to move. That's what you want. That's what I like to see. We already know we can beat it greased without any excess leverage on the handle. Let's just do it again, but let's just make it dry. It's gonna give it a couple good yanks. Ugh. Okay, that's pretty tight. Okay, here we go. Okay, let me tighten the vise up a little bit. What are we up to? 353, here we go. Woo. Please, load cell, stay good. 399. That was pretty stable. That was not wiggling around. Let's take a look at the jaws. You got parts of the socket left in the knurling. Look at that. Man, those look beautiful, don't they? You can't even tell that was crimped right on the edge. For this next test, we're going to be talking about using the vise as a press. A lot of you guys say vices are not presses and they shouldn't be used for that. Well, I beg to differ. This one is. The 510 is designed to be a press. So if you've never seen one of these before, you got a male, female, and then when you turn the handle, you can start to bend material, right? Now these jaws are designed to do 6 inches, maximum 1/8 of an inch mild steel. So for this demonstration, I brought the crew down and I'm gonna have the crew try to bend this piece of flat bar with this vise. Okay, Drew's gonna try to go first. We wanna try to get this to a 90. I want some rules, just don't hurt yourself. Are you getting it?
Not really.
You don't wanna embarrass yourself on camera, but At the same time, don't hurt yourself. Don't release it. Alan, you're up next. Go ahead, bend away, man. Let's go, let's bend.
Nah, it ain't moving.
Wyatt's gonna try to keep going. Okay.
Oh, there you go. Oh, I got it.
Dave, you wanna try? They loosened it up for you a little bit.
No, that didn't move.
All right, I'm jumping in. Ooh, maybe not. Jeez, you guys got that freaking tight. Okay, there's no way. That's about as close as I can get it. No, we barely budged it. Oh gosh, that's so tough. Yeah, that's not gonna make a bracket very well if you can't do that. So that was a complete failure. So let's move the jaws over to the 510 and we're gonna see if it's any different.
You're already past where the other one was at.
Oh, yeah.
I think you got it. I think you did it. Yep, you got it. Pull it out. That's a nice tight bend too. Who wants to try it? Drew? Oh yeah, muscle in it. Boom. That was pretty simple. Alan wants to try? What's neat about this is, as you're watching, we know we're well within the vise parameters because the handle's not bending. Almost got it. A little more, a little more. There you go. There, too much. Overbent it. So this vise could do this all day long, over and over and over again. Okay, Wyatt's gonna finish off what the record couldn't do. There you go. I mean, you gotta work out a little bit, but you don't have to use a cheater bar or anything. So what are we talking here? Let's put some actual numbers to this. Let's throw the load cell on here and see the difference. And I got a long lever on this thing and it is still pretty tough to turn. Whew. To put that into perspective, most people's lug nuts are torqued to 90 to 100. Golly, I hope the vise doesn't break. Okay, there, I think I got it. 226 foot-pounds. Whew, that was quite some effort there. Oh yeah, we definitely bent the handle with my little rig there. Starting to get a wowie in it. Whoa, 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 whoa. We're past its design parameters. All right, let's do the same test again, huh? We want something that bends easy. There we go. Nice, good 90 again. 122 foot-pounds. As you can see, a vise designed to be a press can get you these numbers, which makes it easier on the body, easier to use. The handle's not bent. That's what we want. Now that we've seen what these vices can do, I want to know which one of these will survive some real abuse. To truly be a high-pressure vise, it has to make it through even the toughest work days and still be good to use tomorrow. Some of you might say, that's not fair. You're using a brand new Fireball vise against a vintage used record vise. And you're right. In the real world, your vise doesn't start fresh every day. It carries the battle scars from yesterday's work. So to even the playing field a little bit, let's swap out this brand new Fireball 510 Hardtail for something a little more worn in. In case you haven't seen it, this is the exact same hardtail from our last vise video, where it was pulled through the mud and then pushed to its absolute limits. So let's see if I can put some life back into it. So during the testing, we're trying to get these jaws to misalign and try to snap the head off. And during that process, we bent it. So we need to get the twist back out and point it in the right direction. You can see we're nice and straight to here. And then right here at this point, this jaw starts heading left. So we need to push this jaw right. So currently, because of this bend in this dynamic jaw, it will not slide back into the static jaw. We have to move it that way quite a bit. We also have some damage up here in the jaws. We'll address this later once we get this thing pointed in the right direction. I want to remind everybody, this was a destructive test on purpose. And it's pretty cool that this only bent and didn't snap. And I do think I can repair it. So because we want the jaw now to go that way and this jaw to go this way, as we put pressure over here on this side, this pushes the jaw that way. This side of the arm pushes the static jaw this way. So we're getting opposing forces. It's a serious jack to fix this. See if we can't push this back into submission here. Okay, I'm slowly starting to see it come back. It's one thing I hate about hydraulics is I have no feeling of force. Pressure's coming up. I don't know if I want to go much more than this. That's a 100-ton cylinder with 7,000 pounds of force through it. So I think that's about the best we're gonna get. It's a little sketchy. Let's just back it off. If we can't get it from here, we'll try a different approach. Okay, did we straighten her out? I think we're a little bowed. All right, we're gonna try one more thing. We're gonna try the press. This vise has got a crown in it like that. So I'm gonna try to press it with the 30-ton bottle jack. I don't think it's gonna move it. If not, we'll switch to the heat. Okay, we're gonna give her all she's got here. Not going anywhere. Ugh. Okay, so I think we're gonna have to heat this up. Okay, I'm starting to see it move a little bit. We want the top to contract so it pulls tight. All right, we'll just keep 30 tons on it. So let's just cool it off a little bit up here. We'll just see where it ends up. Sounds like we're making fajitas. We want this to shrink, this to grow. It's a lot of mass there we have to try to bend. All right, it's been a little bit. She's all cooled off. Did she stay? Oof, I don't know. There's only one way to find out. Let's go put it in the vise and see if we got it straightened enough. All right, moment of truth. Oh, dang it. It is bent right there. Okay, well, it doesn't fit. Still a little crowned right here, so I'm gonna put the heat on it. I'm gonna try to shrink it. Okay, we'll let that cool and see what we get. So remember, when heat treating, if you have material, when you heat it up, it likes to expand, but when it returns, it shrinks from its original starting point. Okay, it's cooled off enough to do a test. Hopefully this last heat treat got us back into shape. Whew. Okay, baby. 1, 2, 3. Yes! That is pretty awesome. So now that we have the dynamic jaw fitting in the static jaw, we need to work on the jaws itself. So in the previous tests, we have bolts in here and we've sheared them off. So we gotta get those out. And then we'll run an end mill down here and square the face back up again. First thing we're gonna need is a vise. A vise to hold the vise. I'm gonna try to tap these out and run them around with the chisel. See if that gets them loose first. One, I think the next step is to try to weld a nut to it. See if we can't get it out by doing that. Yeah, ta-da. So all I'm gonna do is side mill until the curve is out of the face. Getting close, just a little bit over there. Another 10, 15 thousandths. So this side is a little high on the floor, so let's just take a skim pass right through there. Next I need to do is, I need to cut this lip back this way just a little bit. This dynamic jaw has a sharp edge. We need to relieve it so that it matches up with the radius of this jaw. This vise is ready to do battle now with the number 6 record vise. So here's how this is gonna work. We have 3 destruction tests. The jaw misalignment test, we have the hammer swivel base test, and the maximum clamping force test. In this corner, we have our Fireball 510. And in the other corner, we have our record vise. But these tests are gonna get destructive. So what happens if we break a vise? That's where my backups come in. Just in case, I picked up 2 more record vises. So if one doesn't survive the test, another can take its place. The Hardtail, however, isn't so lucky. There will be no backups, extra lives, or second chances for the 510. It will have to push through the gauntlet on its own, carrying the battle scars from each test. So first up, we will simulate an object caught between the jaws under torque. This can occur when clamping a square object. In this scenario, one jaw pushes left, while the other jaw pushes right. For this test, we'll put the vice crusher machine to the challenge. This is the same crushing machine that I've built in my previous video. And in that video, the Hardtail pushed over 40,000 pounds of pressure before reaching failure. So let's see if the record can beat that. We got the record vise all mounted to the table. We want to see how this connection of this vise handles the forces involved if you were to try to twist this square. Because if you feel underneath here, it is very thin. There's not a lot holding this whole jaw up. This part of the contraption pushes right here on the side of the vise. The other end pushes on the static jaw. So you're getting opposing forces going like this. We're gonna measure the side load with this probe in the load cell. This will be a test to destruction. We're gonna keep pushing until it breaks. Watching it move. 3,000 pounds, 4,000, 5,000, 6,000, 7,000, 8,000, 9,000. Whoa! Whoa! Wow, look at that. Let's get this out of the way. Whoa! That's quite catastrophic. English steel. Wow. Okay, look at that. I've seen this before in other vices. This lever, see how it's pulling over like that? It just popped it. These are just gray cast iron vices. These are not anything special. These are low pressure vices. This catastrophically failed somewhere around 10,000. We put the same machine in between the jaws of the 510, cranked it up and got it to 40,000+ pounds of side pressure. And all we did was just bend it. And then after that, I fixed it. With the first record vise destroyed, I'm now down $500. Let's replace it and see how it performs in our next test under the hammer. Just like in our previous test videos, we'll put both vices under the hammer. This massive machine is designed to test the swivel base by striking a bar held in the jaws of the vise. So out of the 3 vices, I picked this one to go under the hammer. It has a really good swivel base, and what I'm just looking for is that there's no cracks, damage, or any of the sort that's gonna throw off our data collecting. It's a little dirty, but that's one component. And this whole swivel base is made up of 4 pieces. You got the outer ring, the inner ring, and the 2 nuts. And they all look like they're in very good condition. None of the threads are stripped out. Everything looks great. There's no cracks that I can visibly see. The hardware looks good. Maybe a little bit of thread damage right there, but that's to be expected. This is just what you're gonna get with a used vise. If you notice, this vise doesn't have the original jaws. Somebody's put soft aluminum jaws in its place. This isn't gonna affect our test because when we hold this test bar in between the jaws, we're looking for how it transfers the load down in here to the swivel base. This is the test bar. We're gonna clamp it in here and the hammer hits right there. And we always test at the far edge of the vise because that is where the most load gets experienced from. And we clamp it down as hard as we can. So we got the record vise loaded up. Let's talk about the difference from previous tests that we've done with this hammer. Because the hardtail vise is so strong, and during my continuing testing with it, I've increased the weight so I can get the hardtail to break. It used to weigh 75. This hammer now weighs 100 pounds. So that data may not cross-reference perfectly, but that doesn't matter. The record and the hardtail are gonna be seeing the same hammer weight. So you guys know that I'm not cheating. I'm gonna pull on this handle. Ugh. That's pretty tight. And then I'm gonna bang these things like somebody else already has. Here's my prediction. This vise with its build construction is gonna make it maybe 3 hits. All the cameras are rolling, high-speed cameras rolling, 4 or 5 low-speed cameras. We got GoPros. Okay, everyone's got safety glasses on. We're standing back. Here we go. Okay, the hammer's coming up over the top. 3, 2, 1. Oh, wow. Oh. Okay, wasn't quite expecting that. This was expecting the swivel base to break, not a dynamic jaw. This is a catastrophic failure, which means this vise cannot continue on. This is the difference between high pressure vices and low pressure vices. This is just gray cast iron. This isn't anything fancy. This isn't ductile iron. We do not know how this vise was treated previously in the past. And this is the risk you take when you buy a used vise at a used vise price. That now this money that I spent, this vise cost me 500 bucks, is now trash. I was literally hoping that the swivel base would break because that's replaceable. The vise can still continue to go on. Can't really trust it if you really want to do some banging on it. So why did this break right here? Well, you have to remember this screw is pushing and the jaw is wanting to go backwards. And you can look at the high-speed footage, and when this jaw gets pushed back, you can see it lever forward, right? This wants to go in, this part wants to go back, and see the shear line right there? That's why the hardtail vise has got that shear line at that angle. And if you also look, see how it's right here at the point? This was boxed in, and then at this termination point, you see how it gets hollow? See how this is a 4-sided box? This is the transition to 3 sides. Remember we talked about earlier that 3 sides is bad? That's why. So let's get the record number 6 off and the hardtail on. I'm just gonna tighten these by hand. Give it a good squeeze. Remember, this vise has been the test mule around the workshop. This vise is used and well abused. What do I expect to break? The swivel base. We want the swivel base to break because that's a replaceable component. If you guys would like to see somebody use this vise in practice, go check out Black Bear Forge. He's a YouTuber, he does blacksmithing professionally, and he uses a 614 in his workshop. And he says it's the best vise that he's ever used. I predict that this will take 30, 40 hits before anything happens. Here we go, cameras are rolling, high-speed cameras rolling. Okay, hammer's coming up and over the top. And 3, 2, 1, this is gonna hit hard. Ooh. Ooh. All right, let's hit stop. Let's take a look at what happened. Man, look at the power behind that. Hit that all the way over, came in and dug in there. Man, that thing hit hard. So we just got the first hit. Things that might break are the jaw bolts, because you can see this levering up. So it's trying to lift this jaw up out of there. So those bolts might snap off. Then obviously the swivel base is gonna break, but I think everything else in between is gonna be just fine. Let's keep going. 4, here it goes. Ooh. 5 hits. 10 hits. Let's just take a look. Handles are still fairly tight. This is tilting a little bit, but it's still hanging on there. Tighten it up a little bit. The fact that it's made it 11 hits, quite impressive. This hammer is much bigger than the last one, and you can really feel it in your chest when it hits. Boom! Moves the whole table, your whole body just shakes. Oh, we got something. Something happened there. Jaws are still about the same where they started with. Everything seems to be still operating smoothly. The test bar is absolutely getting annihilated. It's hitting here, and then when it rolls back, it's mushrooming down there. As it pries in the jaws, we are absolutely destroying this bar. Handles, check. Swivel base, check. Good to go. Off we go. I think we're gonna lose the spindle, is what I think, or I think we're gonna break the nut in the back. I think it's stretching. So if you watch the table, it's gonna move back a good 1/4 inch or so, and this is 4,000 plus pounds of table. Oh, I think we got a failure. Or something's loose. Let's hit stop. Okay, what did we lose here? Or did this just, oh, we broke something in the swivel base. Good, this is exactly what I was hoping for. Oh, we broke the center pivot. That would make sense. All that looks good and tight in there. Let's take a look at the bottom. So when these get a little loose, then that takes all the brunt. So I could see why that would break off. Let's take a look at operation. Pretty smooth to me. Screws nice and straight. About the same amount of side to side play as it had before, very little. What I did notice is their jaws, bolts are coming a little loose. So let's tighten those up just for safety. Let's take a look at how the jaws close. Okay, not perfect, because remember, I didn't get it quite perfectly straight when I bent it back, but that's exactly where it was when we first started. So this is the only piece that broke, and this is a replaceable part. So we're gonna conclude that there. We made it to 25 hits. I know we can do way more than that. If we keep going, probably continue to break the swivel base, but we might also damage the screw. I'm not switching this vise out for any of the future tests, but we're gonna switch the record vise out and give it another opportunity to beat this.
The third and final test simulates how much rotational force the vise can withstand when turning the handle. This represents normal operation, putting an object in the vise and squeezing the handle, and sometimes with a cheater bar. This puts stress on the internals of the vise.
We're gonna turn the handle with the torque wrench that's set at 100 foot-pounds. We're gonna watch the readout and see where it stops. We have the meter set to peak, so whatever we see, that's the highest number that the load cell has recorded at that moment in time. We have a little preload in the vise already. I'm also gonna be looking at jaw deflection. How much has the jaw tilted over at whatever force that measures on the load, okay? And we're gonna do that with this dial indicator that's set right here on the other side of the jaws. Cranking, let's see, 400, 500, 1,000, 1,600, 28, 4,000, 100. Oh, not getting any tighter. Oh, come on, there we go, 5,000, 5,700. Oh. We'll just call it 6,100. We'll give it the benefit of the doubt. I think I pulled it a little bit past the click. Okay, so it's deflected 50 thousandths of an inch. So everything's loaded at 6,100 pounds. Now I'm just gonna keep cranking with the cheater bar, and we're gonna go till the handle bends, and we're gonna record that number. Here we go. Okay, meter's going up. I'm just gonna wrap this sucker around. 13, 14, we're getting close to where we ended last time.
It's about to go
Where are we at? 16,000. Ooh. I knew we were close. Wow. And that's, folks, how you break a vise.
Boy, the handle's not even bent. Okay, well that was kind of disappointing. It broke at 16,000. Look at that. Almost identical to where it broke before. So there's the handle, barely has a bend in it. So that's not very good, is it? So the window between vise breaking and handle bending is too close. There needs to be more safety margin between those 2 points. This handle is too big in diameter for this vise. Okay, let's get this record off the stand. Let's load up the 510 to go through the same test. But there's little differences. I have increased the jaw capacity from 8, like we had it before, to 10. So that is another disadvantage to this vise, is that we have more leverage because we're opened larger. But everything else is the same. I made sure to tie off my dial indicator this time. I don't want that hitting the floor. So everybody knows the rules. 100 foot-pounds of input torque. I have a little preload already on the load cell, just from the weight of everything. All right, so here we go. We're already up to 4,000, 5,000, 8,000, 10,000, 11,530, which is about in line with what we've seen before. That's pretty good. What do we deflect? Looks like 37 thousandths of an inch. So I'm just gonna pull this with my hand and we're gonna see where we're at, okay, before we switch to the cheater bar. 15, 16, 17, 18, 19, 19.2. I could probably refine a little bit more, but remember that other record vise just completely shattered at that point, and I just pulled that with this handle. I gotta see 20, right? Okay, 20. So we're deflecting 75 thousandths at max opening at 20,000 pounds. So now let's bend the handle. We're gonna put the cheater bar on it, and if you noticed, this vise handle has some reductions in diameter. I want to see this bend first to give me an indicator to stop what I'm doing. This handle is protecting the thrust bearings, the screw, the nut, the jaws. It's protecting everything. So let's bend it. All right, here we go. Go to the handle bends. 25. Good. That's exactly what I wanted to see. It told me to stop what I'm doing, you moron. Okay, everything's still intact. The vise is still working. So technically I could reverse this and keep going to work. We're still operating between that 15 and 30,000 pounds of pressure. So we've deflected what, 26 thousandths. So here's what we're gonna do. Nobody in their right mind would put another bar in here, keep going, trying to twist. But what they could do is put a hydraulic jack in between the jaws and use it like a press. Say hello to my little friend. 50-ton hydraulic press. You know it's a good day when you have to break out a hydraulic jack to break the vise. The last time I did this jack fell on the floor, made a dent in the concrete, so I have tied it up this time. It probably will break a component that we could replace really easily, and then we could be back and running again. Got the load cell in between. The load cell's all the way up to the left. Let's break it. Get some pumping action coming up. Okay, 29, 30,000. 32, 33, 34, 37, 30, 40, 47, 48, 50,000, 54, 55, 55,000 pounds. It's not going no more. Something's going on with the jack. Woo, that is scary. It's holding at 55,000 pounds of force. But I would say at this point in time, the vise is no longer usable. So I say we just call that good. But that's a ticking time bomb. Last time I got this close, we know what happened. Boom! Whoa, dude. So here's what we got. The vise is holding at 55,000 pounds. Obviously it's not working anymore, it's all bent. But I wanna see how long it can hold it for. Maybe 10 minutes, 20 minutes, 30 minutes, an hour. We're just gonna take a step back and we're gonna monitor it and see what happens. So if you noticed with the record vices, how it just exploded. There was no warning, there wasn't anything that was an indicator of this gonna fail. It just poof, popped. That's a good indicator of gray cast iron. This is ductile cast iron, which is basically mild steel. This is a steel vise, and you can see it has elasticity. It bends before it fails. This is what makes this vise safe, being a high pressure vise. The gray iron vices, they just pop and explode right in your face, and that can be pretty dangerous. Okay, so it's been over 30 minutes, probably about 35 to be exact. This thing's been holding pressure. I don't think anything's gonna happen to it. So let's release the pressure and look at the damage. See? Oof. Goes down, down, down. It's crazy that it still works. Does it still go down? Okay, she's not as good as she once was. It's a little chunky, but it didn't blow up in my face. That's pretty impressive. So previously, this jack popped the 614. This jack then fell on the floor. Something might have happened to it inside there. This jack should be outputting 100 tons. But realistically, this vise is done for anyway, so at 55,000 pounds, I think we found the limit. I want to remind everybody, this vise took 45,000 pounds left, 45,000 pounds right, dragged behind the truck, 30 tons to bend it straight, heat in this area to get it all straightened back up. Hammer blow, hammer blow, hammer blow. Torque, 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 torque. This is one serious unit. That's why this is a high pressure vise. So there you have it, 3 record vices versus 1 fireball hardtail vise. The record vise is a low pressure vise. It's great at sharpening lawnmower blades, fly tying, anything hobbyist would do. I think it works perfect for that. This is a high pressure vise. It's designed to throw anything you want at it in a high stakes environment where you need lots of clamping force. You want to use it as a press. You want to hammer on it. You want to beat on it. You need to rely on it. This is why this price is the way it is, because this vise is designed not for today, but tomorrow and the next 100 years. And I think that's the big difference. So when you say, Jason, this vise is more money, well, I think it's highly capable. So that's why the price is the way it is. 3 record vices versus 1 hardtail. You guys tell me which one's the best down in the comments below. Tell me which vise you want to see tested next up against the fireball hardtail, and we'll do it right here. We'll throw it under the hammer. We'll go through the tests again because this is really fun. I love all this information. So until then, I'll see you guys on the next one.